All right. Homework 19, expected outcomes and probability. All right, an insurance policy sells for $1,000. Based on past data, an average of 1 in 100 policyholders will file a claim for 20,000, 1 in 250, 50,000, 1 in 400, 80,000. Find the expected value to the company per policy sold if the company sells 20,000 policies. All right, so an insurance company sells a policy for $1,000. I'm just going to write that at the top. And let's go ahead and see what the expected payout is. So we're going to use these probabilities in conjunction with the expected payout to compute how much coverage do we have for that insurance policy. And by coverage, I mean, is this $1,000 enough to cover the expected payout if 1 in 100 policyholders will file a claim for 20,000, 1 in 250 for 50,000, 1 in 400 for 80,000. So expected pay expected payout. So we have 1 in 100 will file a claim for 20,000 plus the expected payout for the 1 in 250 that will file a claim for 50,000. One in 400 will file a claim for 80,000. Okay, so we need to crunch these numbers. So we can do some simplification beforehand. So we can cast out some zeros. 1, 2, 1, 2. So this becomes 200 plus, cast out a 0, 5,000 over 25. 5,000 over 25 would be 10,000 over 50, which would be 1,000 over 5. Which would be 200. Did I do that right? 5,000. 200. Cast out zeros. 1, 2, 1, 2. I have 800 over 4. So that'd be 4 over 2. So that'd be another 200. 2, 4, 6. Okay, so the expected payout for each policy sold for $1,000, we expect to lose $600 from people filing claims. So the expected value here, what they're looking for, is what is the expected value to the company for each $1,000 policy sold. So for each $1,000 policy sold, you have to put $600 on hand for the potential payout. So that leaves you with a value of 400. That means for every $1,000 policy sold, the company can safely assume that they have yielded $400. The expected profit, so loss or profit, this number is positive, so we're calculating a profit. If the expected value is negative, it would be a loss. So it is going to be a profit, and well, what the hell is the profit? Where is it coming from? Well, we make $400 for every policy sold, and we sell 20,000 policies, so 20,000 by 400. 1, 2, 3, 1, 2, 3, 8 million. So the expected prophecy is 8 million. Moment of truth. All right. So this is the basics for doing an expected payout. You're taking a probability and you're multiplying it by the potential payout. So probability multiplied by the potential payout, and then we do that for every potential claim that could be filed. add up the sum, gives you a number, and then recognize, well, this number represents the amount of money that has to be set aside for every policy sold. So each policy sells for 1,000. We need to set 600 aside for every policy. So that means we gain 400 for every policy sold. Multiply 400 by the number of policies sold to get the total profit. All right, so let's jump into this one. Suppose you play a coin toss game. You get $1 every time heads appears. You get $1, or you lose $1 every time tails appears. First 100 coin tosses, heads comes up 36 times and tails comes up 64 times. All right, what percentage of times has heads come up in the first 100 tosses? Well, recognize heads showed up 36 times out of the 100 tosses, so the percent is going to be 36 times out of 100 total times to give you 0.36 as a decimal. Multiply this decimal by 100 to see the percent of 36. All right. What is your net gain or loss at this point? Select the correct choice and fill in the answer box to complete your choice. Okay, so, well, we gain $1 every time heads appears. We lose $1 every time tails appears. So we gained $36, right? We get $1 every time heads appears. We lost $64 every time tails appears. We lost $1 every time heads appears. We gained $1. Taking the difference, 64 minus 36, 28. So recognize we lost more than we made. So we lost $28. You could also look at this as we lost, and this is going to be a bit of a double negative, but here's a better way to look at it. Think of these losses as a negative, and then add these two numbers. So 36 plus negative 64 would give you a negative 28. So that tells you you lost $28. So don't put in you lost negative 28. It's a double negative at that point. So you lost $28. Move my green arrow box up here. All right. Scroll down for you. Suppose you toss the coin 200 more times, a total of 300 tosses, and at that point, heads has come up 37% of the time. Is this change in the percent of heads consistent with the law of large numbers? So recognize we went from 36% being heads when we flipped it 100 times. When we flip it 300 times, we see 37% were heads. We would expect, just from our gut, that if you toss the coin 300 times, that roughly 50% would be heads. So kind of set that thought aside for the moment and consider that, well, the percent of heads increased from 36 to 37. So the percent of heads is approaching 50%. It's not doing it very quickly. It's gone from 36 to 37, so it's only gone up 1%. However, 37% is closer to 50% than 36% is. So we would say that this is consistent with the law of large numbers, because the more times you flip this coin, the closer this percent should get to 50%. Why 50%? Well, that's a theoretical probability of flipping a head with a fair coin. So the change is consistent, the change is consistent, not consistent, not consistent. So C and D, no thanks. A and B, The change is consistent with the law of large numbers because the percentage is low the first 100 trials. It has to be higher the next 200 trials to even out. It doesn't have to do anything. So A is not looking very promising. B, the change is consistent with the law of large numbers because as the number of trials increases, the proportion should grow closer to 50%. Absolutely. All right. What is your net gain or loss at this point? Select the correct choice below and fill in the blank. Well, 300 tosses. So 300 tosses. And we're told 37% heads. Well, that would mean 63% were tails. 37% were heads. Well, we gained to figure out what we gained, we need to take 37% of 300, so that would be 0.37 multiplied by 300. 111. .63 times 300, 189. So again, we can think of this loss as a negative, and if we add 111 plus a negative 189, we get negative 78. So this negative 78 is coming from 111 plus a negative 189. Adding a negative is the same as subtraction, just to let you know. So negative $78, that would be a loss of $78. Zoom in for you guys. How many heads would you expect, or how many heads would you need in the next 100 tosses in order to break even after 400 tosses? Is this likely to occur? Select the correct choice and fill in the answer box to complete your choice. Okay. So how many heads in the next 100 tosses to break even? So, okay, consider the fact that breaking even after 400 tosses would be an equal amount of gains to losses. So, get a fresh piece of paper. So, 400 tosses. Break even. Well, breaking even means 200 heads and 200 tails. And so, as of 300 tosses, so we see from before with the 300 tosses, we had 111 heads and 189 tails. So I'm going to focus on this 200 heads. So to break even, I need to toss 200 heads. As of 300 tosses, I tossed 111 of those heads. So when this question says in the next 100 tosses, so between the 300 and the 400 tosses, there's my next 100. And I need to flip. Well, I started with 111 heads, and I need 200 heads. So 200 minus 111, 79. 200 minus 111, 89. I'm sorry. So I need to flip 89 more heads in the next 100 tosses. So, quick little breakdown. We want to break even after 400 tosses, which means I have to flip 200 heads and 200 tails. From the previous problem statement, I knew from after 300 tosses, I had exactly 111 heads. So this leaves 89 heads to be flipped to break even at my 200. And these 89 heads need to occur within the next 100 tosses. So recognize flipping 89 heads out of 100 tosses is not very likely. So how many heads would you need in the next 100 tosses to break even after 400 tosses? Well, that's our 89. So you would need to toss 89 heads. You would need to toss 89 heads. This is likely because it is close to the expected number of heads. This is unlikely as it is far from the expected number of heads. This is likely because so few heads have been tossed so far. So B is kind of the obvious choice, just because it's the only one where it says this is unlikely. And why is this unlikely? Well, out of 100 tosses, you have to flip 89 heads. Not very likely. You would expect somewhere around 50 heads, right? Exactly half of your tosses would be heads. 89 it's almost 90% heads. So hence it is unlucky, or not unlucky, unlikely. So we need to toss 89 heads. Sorry, I'll try to speed this up a little bit. Check answer. All right. Last one of this. Suppose that, still behind after 400 tosses, you decide to keep playing because you are due for a winning streak. Explain how this belief would illustrate the gambler's fallacy. So the gambler's fallacy in its essence says, if you have a string of bad luck, it's a fallacy to think you will have good luck in the future. If you have a string of good luck, it's a fallacy to think you have bad luck in the future. And that's because if you flip, so just real quick, if you flip a string of heads, 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 heads. So you flip 1, 2, 3, 4, 5, 6, 7 heads in a row. Pretty amazing feat. And then I ask you, well, what's the probability on your next toss that you would flip a head? Well, it's still going to be probability of a half. So a string of heads does not say that you're more likely to flip a tails in the future, or vice versa. A string of tails doesn't mean that you're more likely to flip a head. Or if you flip a string of heads, don't think that the next flip is more likely to be a head or a tails. So each event, each one of these 7 original tosses all have a probability of a half. So even though you interpret this as a string of heads and you might anticipate a tails to be more likely, a tails still has a probability of a half. So this illustrates the gambler's fallacy because due to the law of large numbers, the probability of getting heads must now be more than a half. Because the number of heads cannot be under 50%, because the probability of getting heads is always 0.5, because eventually there will be a winning streak. There doesn't have to be a winning streak. C seems promising. And in fact, so I guess, yeah, let's go ahead and finish this. This illustrates the Gallmer's fallacy because the probability of getting heads is always a half. Seems promising. Cannot be under 50% all the time. Yes, it can. Law of large numbers, the probability of getting heads must now be more than a half. No. Okay, so C seems like the best choice. Moment of truth. All right, and we got it. Okay, so that finishes up the expected outcome. Thank you for your attention. I'll see you on the next one.